hewing and forking around. So. All right, so we'll continue with our discussion in relations. So I'm guessing by the end of today's lecture, we'll be done with relations. So you guys will get a new homework assignment that's going to be due on next Wednesday for relations. Are there any questions about the one on functions? Does anyone have any questions about the 1, 2, 4 thing? No? Okay. Any questions about the announcement that I sent over the weekend, where some of the questions have missing open parentheses? No questions about that one. Okay, it should be fairly obvious, but I just want to make sure that you guys all understand that there's a little bit of typo in the questions. It depends on when you open your quiz, because if you open your quiz later, you may not see that because I would have fixed that already. So. All right, so let's go ahead and get started with relations. So we're getting back to relations, because we talked about it last week already. And we talked about, I think, all 4 of these attributes. So, instead of pointing to, the convoluted, math equation thing that describes what each one means, so I'm just going to test you, okay? Quick, quiz that doesn't count to your grade. What makes okay, first of all, if I have a set X, okay, and I say there's a relation R defined over X, what is R? It has to be a subset of what? X cross X, very good. It's the Cartesian product of X and X itself, so the relation has to be a subset of that. It can be equal to, if you have a full relation, that's fine. It can also be an empty relation. So a relation can be an empty set when nothing in a set relates to anything else in a set. That's entirely possible. All right, so getting back to these 5 terms, reflexive means every element in a set relates to itself through a relation. So basically you have to find 2 tuples inside the relation itself, where you find an element and itself. So those have to be in the set. You can have additional elements in the relation. Okay, so the elements inside the set X can relate to other things, but they all have to relate to themselves first. That's reflexive. The second one is symmetric. Symmetric means if you have AB as a 2 tuple in a relation, then BA also has to be there. If AB is missing, then BA also has to be missing. So they come in pairs basically, except for the things that also contributes to reflexivity. So if you have AA, then obviously AA is the same thing as AA when you have it being symmetric. So are we good with 5.1 and 5.2? Are there any questions about what makes a relation reflexive and what makes a relation symmetric? Okay. So 5.3 is transitive. Okay, what makes a relation transitive? The best example of a relation that is transitive is less than defined over integers. If A is less than B and B is less than C, then A is less than C. Okay, that's basically reflexive. But you have to be careful because, excuse me, I said reflexive, but I meant transitive. So that's transitive. But you also have to be careful because an empty relation is symmetric. Okay, because in an empty relation, AB is missing. Well, so is BA. So that means an empty relation is automatically symmetric. An empty relation is also automatically transitive because AB is missing, BC is also missing. Well, if at least one of those 2 is missing, then the conjunction is false. If the conjunction is false on the left-hand side of an implication, then the whole implication is true. So for that, maybe it's better to look at the definition. See this implication here? That's the key. because this implication basically says if this conjunction is false, then I don't really need to know whether this is there or not. So in an empty relation, this is going to be false, and this is going to be false regardless of how you choose E, F, and G. So as a result, your conjunction is going to be false, but if your conjunction is false, that automatically makes the implication true, because X implies Y is the same thing as not X or Y. If X is false, the whole thing is automatically true. Is that okay? The last one is antisymmetric. And this is how antisymmetric is defined. It basically says, for any two elements in X, for any way to choose two elements in X, if EF is in R and FE is also in R, that implies E and F are the same. So one good example to illustrate this is less than or equal to. Because in integers, if A is less than or equal to B, and B is less than or equal to A, then guess what? A and B must be the same. So that is a relation where it is antisymmetric. Now, less than or equal to is not only antisymmetric, it is also transitive, right? It is also reflexive, because every value, every integer is less than or equal to itself. It is not symmetric. Does it make sense? 3 is less than or equal to 5, but 5 is not less than or equal to 3. Is that all right? So with all of these, we can finally define what is partial ordering, or what is how we define partial order. So a particular set X is said to be partially ordered by a relation R if and only if all of the following are true. Okay, so it's not just one, but you need all of these to be true, or you can also look at it as the conjunction of the three being true. So R has to be reflexive, R has to be antisymmetric, R also has to be transitive. Did I just mention a relation that meets all three requirements? Less than or equal to. So less than or equal to turns out to be partially ordered. Is that okay? And that's just how it's defined, okay? So if you read on the text here, partially ordering is kind of important, but it is not as good as totally ordered. Okay, partially ordered means there are certain things where you cannot determine the order. Now, when you look at integers and you look at less than or equal to, obviously everything is ordered. Okay, give me any two integers and I can tell you whether or not one integer is less than or equal to another integer. But just being partially ordered doesn't mean that a particular relation can tell you the ordering between every two elements of X here as a set. So what we'll do is I'm going to copy, without any type of reference to the beer, a commercial. So I'm going to scroll to this top here. How many people remember that, I think it's an Australian beer commercial, where the premise is they show two examples of rich and smooth, and particularly this is back in the day when it's kind of gender biased. Okay, so it talks about a guy who is smooth but not rich, another guy who is rich but not smooth, but the beer itself obviously is rich and smooth at the same time. Do you guys remember that? No? I think we should watch that commercial. You don't know what it is? Okay, beer commercial, rich, smooth. That should find it, right? Okay, so 20 commercial, that's totally nailed it. There we go. I think this is the one. Let me, now, oh, you guys can actually see the full screen. Okay. And let me rewind it. with closed captioning, right? Oh, you guys cannot see the closed captioning. So maybe full screen doesn't work. And I'm trying to make it so that you can, what is that? Mini player. Yeah, they're actually in the Best Buy kind of store. So now here's the beer that is both rich and smooth. Okay, so are you guys getting it? Okay. So how does a beer commercial have anything to do with the class, where the campus does not even allow you to bring anything that's alcoholic, right? That's funny. You just immediately put down your container. It's like, oop, okay. Okay. So we'll just kind of use the ordering, like, which is more desirable, okay? So of course, this is making an assumption, okay, that both rich and smooth are desirable, and being both is more desirable than being just one or the other or none at all, okay? So it's based on a bunch of assumptions. So we'll basically just go through this list here, okay? Rich and smooth and rich is more desirable than smooth but not rich. Smooth and rich is more desirable than not rich, not smooth but rich, okay? Because one is missing on this side and this side has both. And certainly smooth and rich is more desirable than not smooth and not rich, okay? And then here we have smooth and not rich is more desirable than not smooth and not rich. Not smooth and rich is more desirable than not smooth and rich. Is that okay? So is that kind of following the logic of that beer commercial? Okay. So in the beer commercial, they only showed what is smooth and rich, which is the beer. They also showed what is rich but not smooth, which is the first guy. And then they showed what is not rich but smooth, which is the second guy, the guy who went to Best Buy as his like personal living room. But they didn't show what is not smooth and not rich. So just to finish and complete the visual picture, I volunteer myself. So now you have the complete picture, okay? So now what we're going to do is to say, but do we have partial ordering? Do we have total ordering? Okay, those are the questions. So instead of asking what is more desirable, because it does not include equal to, we're going to ask a different question. So I have this abbreviation, at least as desirable as, and I'll just turn it into an acronym, which is ALADA. Oops, just dropped one of the mics. Definitely not smooth. Okay, so we have this at least as desirable as, which is simplified as ALADA. Okay, so ALADA is our R. That's our relation. Okay, and then these qualifications are our elements. They are the elements in the set X. So we want to find out whether ALADA as a relation is partially ordered or not. So we basically generate a whole bunch of new relations as follows. Okay, so it's a little bit longer than before, but I think it makes sense. So rich and smooth is at least as desirable as rich and smooth, which is to itself, right? It makes sense. It is the same qualification, so it is at least as desirable as the same qualification. So we just follow this list here and generate basically the rest. But you can see the additional items here. Instead of asking whether it is more desirable, instead we ask, is it at least as desirable as, it is now reflexive. See how it is reflexive? The first item is required for being reflexive. This item here is also required for being reflexive. Smooth and not rich is at least as desirable as smooth and not rich, which is itself. And then we move on to here. This is also required for being reflexive. Not smooth and rich is at least as desirable as not smooth and rich, which is relating to itself. And then last, we have not smooth and not rich is ALADA, not smooth, and not rich, which is also relating to itself. So now we have a relation that is at least reflexive. Are we good so far? Next question, is it transitive? Well, let's check it out. Let's see, smooth and rich is at least as desirable as smooth but not rich, okay? Then we look up smooth but not rich, right here. So we say smooth and not rich is at least as desirable as not rich, not smooth, and not rich. So now we have the left-hand side of the implication in transitive. So now the question is smooth and rich alada, not smooth and not rich? So you look this up, and here we got it. Smooth and rich is alada, not smooth and not rich. That tells us that this is transitive. It's just one of the examples, but it does show us that it is transitive. Is that okay? So what is the last requirement for something to be partially ordered? Antisymmetric, where you say, okay, A are B and B are A means they are the same. Okay? Do we see that here? Yep. So it's also antisymmetric. We see it here because we have this item, and then we have basically everything that relates to self. We got this item, we got this item, and then we also got this item here. Are we good so far? But that means, does that mean everything that is reflexive automatically antisymmetric? Nope, it does not mean that it is the same. I will give you an example. So I'm gonna switch gear here and use basically a notepad to give you an example where something is reflexive, but it is not antisymmetric. So here's X. So we'll just use A, B, C in the set, and then here's R. So this is our relation. So we have AA, BB, and CC. But I'll just add one more thing that will make it two more things to make it not antisymmetric, assuming B and A are different. Okay, so okay, I have to close with the correct bracket here, brace. There we go. So this particular relation is reflexive because every element relates to itself. It is symmetric because you can see AB and BA are both in it. But it is not antisymmetric because AB and BA are both in the relation, but A does not equal to B. That disqualifies this R as being antisymmetric. Okay, so before we do that, it might be helpful to kind of go back to the definition of antisymmetric first. So I'm going to keep this on the side and scroll back to antisymmetric, which is this particular definition. So, and then we show the the set X and also the relation R. And now we ask the question, is R anti-reflexive, antisymmetric? In other words, is this condition true for every way to pick two elements out of X? And it turns out to be not the case. What if I pick A to be E and I pick B to be F? Let's see what happens. AB is an element of R. BA is also an element of R. So we have a conjunction. The conjunction itself is true, right? So we now have the entire left-hand side of an implication being true. But does A equal to B? Nope. So that means, for at least one element in the relation, for at least one way of picking two elements out of X in the relation, this condition is false. So that's why it is not antisymmetric. Is that okay? All right. But does that apply to our example here? It does not apply to our example because our example is not symmetric. So if it is not symmetric, we don't have to worry. Well, okay, I shouldn't say that, but it definitely does not have that particular element where one thing relates to the other thing is related to the first thing, where they are not the same. We do not find an example to make it not anti-symmetric. Is that okay? So are we reasonably convinced that this particular example is partially ordered? So what is the big deal again? Well, the big deal is we cannot find out the ordering between smooth and not rich and not smooth and rich. Those two cannot be related. We do not know which one is at least as desirable as the other one. It is not confirmed one way or another. Is that okay? But then you can say, well, doesn't that mean that smooth and not rich is not at least as desirable as not smooth and rich, and so on with the other one? Yes, you can claim that. But in order for something to be fully ordered, at least one direction has to be true. Whereas in this case, neither direction is true. You just cannot confirm the ordering. Is that okay? So, maybe? It's good? Okay. So what is the application of this stuff in actual programming? I mean, the best way to learn something like this in a class is not to focus on just the theory or the definition of terms, but to think about it in actual programming. Why do I need to care about this in real programming? Yep.
For the stuff we're missing, if we have that, can we sort it?
Yep, exactly. But why do you care whether something can be sorted or not? Oh, you can rank, right? You can rank things. So what we'll do is I'm going to give you an example, okay? So I'm going to define a structure called stat, okay? You can look at a struct as a class, okay? I'm just a C programmer and not that much of a C++ programmer. So I'm defining stat as a structure. And within that, we have two unsigned integers. Let's see, what is the kill something ratio in most video games? KDR, kill death ratio, KDR, okay? So we have a KDR probably expressed as a double, okay? Double precision floating point number. That's one stat that may be useful, right? Give me another stat that is also useful in video games. KDR is one. Maybe a win ratio, assists, or time played. I like that, okay? So time played, okay, can be useful as well. Okay, so now we got two metrics, in the stat of a particular player, and we want to find out, okay, how do we find the player of the week, given that we have a list of players, and for each player, there are these two metrics. They go like, well, we got two numbers, and less than or equal to is not defined when you have two numbers. So you kind of have to define your own operator, of less than or equal to. Does that make sense? Okay. So we'll go ahead and define that. So we'll say less than or equal to, and we have stat P1, the pointer to the first stat, and then pointer to the second stat. And I just need to know which one is less than the other one. That's all I need. Okay? So how do we do this? Well, there are several ways to do it. Okay? So we can return something, and to make it so that So we can return P1 KDR is less than P2 KDR, or P1 time played is less than P2 time played. Okay. Are we good so far? Yep. Well, because it's just, an int is the same thing as a boolean. C99 does not have bool, so you have to use an int. I think so. I think C99, or C standard, ANSI standard for 1999 does not have boolean as a type. Well, I mean, C was never intended as an actual, programming language. It's intended as a tool for two, expert programmers to be used by themselves. Actually, I want this to be I'm just thinking whether it should be an and or. I think we want it to be an and. There we go. Okay, so change that to an and. So now I can say this, so now we want to find out whether this is partially ordering or not. Why is this important? Because if I want to use this as a function to determine the ordering, of a list of people, so I can find the player of the month, okay, that needs to be totally ordered. For a relation that is only partially ordered, you may not have a single person who is the player of the month. Okay? So now we have to kind of go through a few cases and go like, okay, but is this partially ordered or is it totally ordered? In other words, can we have two cases, two stats, where neither is less than or equal to the other one? What do you think? Can we end up with a case like that? Okay, so let's just this is player 1 and this is player 2, and we want to look at their attributes. So we have attribute KDR, and then we have the attribute of time played. Okay, so can someone give me an example where there's no ordering between player 1 or player 2? You just have to make it so that, no, you have to make it so that it's one player is less than the other player on 1, but greater than in the second metric. So let's say player 1 has a KDR of 0, which is terrible, right? And player 2 has a KDR of 5. And then in terms of time played, player 1 had played 120 hours in that month. That is totally terrible, right? And then player 2 only played 1 hour. Okay? All of these are fictional, obviously. Okay? But in this case, if you use this as less than or equal to, then you cannot say player 1 is less than or equal to player 2 or not. Why not? Because there's a conjunction here. Either way you compare, only one of the less than is true. The other less than is guaranteed false. I made sure by choosing these numbers. Okay? So that's why it's not. So now, if you cannot say whether player 1 is less than or equal to player 2, and whether player 2 is less than or equal to player 1, how do you choose your player of the month if you only got these two players? I mean, they're both good, right? I mean, player 2 obviously is a better player, but player 1 is better from the perspective of the game company. Spends more time, probably spend more money on skins and useless items and whatnot, right? So from the perspective of the game company, I would use player 1 as player of the month, but that would definitely upset player 2. But if I choose player 2 as player of the month, it's going to upset player 1. At least the way I define less than or equal to. Yes?
So couldn't you also not know the ordering if both players have the same exact stats?
If they have exactly the same stats, then they are not, the relation is not true either way either. So that means it is not even anti-symmetric. So the relation that I have defined here is not even anti-symmetric. So you're absolutely right. So that's good observation. So to make it anti-symmetric at least, okay, we can, that's an easy one to fix because we can just say less than or equal to here and also less than or equal to here. Then it is anti-reflexive and also automatically reflexive because of that. But it is still only partially ordered because I still cannot rank player 1 and player 2 in this example. So this is an example to show you why it is important to understand what is partially ordered as opposed to totally ordered. Because what are the chances that you might have to write code to rank something, to find the most of something, the least of something? Pretty likely, right? But what are the chances that what you want to sort or what you want to rank is really just a single number? Probably not, right? Give you an example. Does anyone know, how desirable programmers are in the financial world? Like, people who invest money, people who try to use programs and algorithms to find out what to invest, how much to buy, when to sell, and so on and so forth. There's big money in it. Don't you think you have some ranking to do? And don't you think you have more than one metric per mutual fund or per company, per stock? Well, this comes in handy. Understanding, whether the way you compare those alternatives is partially ordered only or whether it's totally ordered can become important. Because if you think this function is totally ordered, but you use it in the case, you think it is totally ordered, but it's actually only partially ordered, but you use it in the context where it needs to be totally ordered, then what you are recommending to the clients can be faulty. Does it make sense? Yep.
So what's partially ordered won't necessarily work out in a lot of real life scenarios because you're going to have too many things that seem to be equal to each other, but they're not.
They are, you just cannot find the ordering between those items. So you basically end up with a bunch of stuff that is in an array. They're all right next to each other, okay? So because they're equal, in terms of ranking, but there's no ordering amongst them when there should be some kind of ordering amongst them. So you may end up with 120 stocks, for instance, okay? 5 are totally terrible, and according to your sorting algorithm or your comparison, function, those 5 is like dead bottom, okay? Don't buy these. Of the 115 remaining, on the other hand, your comparison, function can basically end up with no ordering between those 115, even though it's clear that within the 115, some have to be better than the other ones, right? So in that case, after you quote unquote sort the array using this particular function for comparing, those 115 items, the ordering between those 115 items does not reflect, whether one stock is actually better than the other or not. But it looks like it is okay. Because your sorting algorithm is not going to break because you give it a function that is not totally ordered. It will still get the job done. It just doesn't give you the correct ranking, in the end. So is that okay? Is that example kind of illustrating how this type of concept relates to programming? Okay, all right, cool. So the last part talks about totally ordered or total ordering. So partially ordered is required for something to be totally ordered. So totally ordered has basically the same requirements as partially ordered. It has to be reflexive, has to be anti-symmetric, has to be transitive, but it has one extra requirement. The one extra requirement is comparable over X. What does that mean? What does it mean when R is comparable over X? It's defined by this thing here. So let me highlight it so that we can talk about it a little bit here. So it basically says if I pick any two things out of X, can be the same thing, can be different things, it doesn't matter. Okay, for every way I can pick two things out of X, ERF or FRE, which basically means they have to relate at least in one direction. So that means out of two stock, okay, that I choose out of the array, any two stock, you have to be able to tell me which one is less than or equal to the other one. Okay? Out of two players, okay, you have to tell me which one is less than or equal to the other one. It has to be true one way or the other. Cannot be false in either direction. Can it be true in both directions? Yes, if they turn out to be the same thing. Because remember, we still need R to be reflexive. So it is possible that you choose E and F being the same element in X, then both of these are true at the same time. Is that okay? Yep. Well, let's find out. Okay, so the question is the empty set considered totally ordered? We know it's partially ordered. Okay? Okay, no, I take it back. It depends on what your X is. If your X is non-empty, then an empty relation is automatically not partially ordered because it is not reflexive. Yep. Any other questions? So I think what you meant is if you have a non-empty X and your R is just barely reflexive, is it totally ordered? Is that kind of what you're asking? Maybe?
I didn't think that far into it. I was just curious.
Okay, so let's try to answer the question. Okay, so I'm going to post the question here. Okay, so given that X is non-empty, R is barely reflexive. Okay, so now the question is R partially ordered? That is the question.
I thought his question was if both X and R are empty.
If both X and R are empty,
Then that's totally ordered. I thought that was.
then it is totally ordered. Yep. But this is a trickier one. So given that X is non-empty, so we got elements in X, and R is barely reflexive, which means it has the minimum number of elements to make it reflexive. Okay? Is it partially ordered? Well, let's see. So we know it is reflexive, right? Because it is minimally reflexive. So we know that much. The next one is it transitive? Transitive. It is transitive. Okay? Because every element is only related to itself, which means the only way you can pick out things, from the set, it would be things that are relating to itself. So the left-hand side of transitive, is either false or it's going to make the entire thing true because you pick the same all three variables map to the same element when you pick those three elements. The last one is anti-symmetric. Symmetric. Is it true or false? It is guaranteed true because the only way I can pick something out of the relation R would be the tuples where the first and the second items are the same because it is minimally reflexive. So it is also anti-symmetric at the same time, which means it is also partially ordered. But then is this R also totally ordered? That's the question. The answer is it is not totally ordered. Because of the many ways you can pick two things out of the set, the OR is going to be false for most of them. Let me go back to the definition of comparable. Unless unless X has only one element. That would be the only exception to the rule. So if X has more than one element, then you cannot make this true. But if X only has one element, then yes, it is also totally ordered. Does it make sense? Okay, let me pose the question in a separate way. If X only has one single element, how big can R be? One element, exactly. It's not a very useful scenario to consider, but just for the sake of theoretical observation or speculation, we kind of have to understand that one. So are we good so far with all this stuff? Okay. All right. So for the next half hour or so, we're going to start a new topic. We're going to move into propositional logic, okay, which is kind of a chunky part of this class in the sense that it is a little bit messy. I like this icon. I like this tab sleeping. So let's wake up the tab here. See, it actually blinks the eye first, before it opens up. Kind of cool. All right, so in terms of the notes, I'm just going in the same order as it is presented on the website. On Wednesday, I'm going to release the relations, homework, but it's not going to be released on Wednesday, so that means, you have 1 week from Wednesday to get it done. It's kind of the same format as the functions assignment, where it's just a quiz where, you have a whole week to work on it. So we're going to move on to propositional logic. And this one it takes a little bit of time to explain, okay? So if you guys have any questions, do not hesitate to ask, okay? So ask for clarifications. So we'll first have to explain what a proposition is. A proposition is explained here. So a proposition is a condition, that can be true or false. That's a proposition. So, there are many things that can be true or false. It's going to rain today, later. Well, it's either true or false, right? Or there's an exam in Calc 1 tomorrow. It can be true or false, maybe not, okay? So all of those are basically propositions. Propositional logic is a logic system that can prove whether a particular proposition is true or false using a somewhat mechanical method. In other words, if I tell you, okay, let me present an example. You go to McDonald's, okay, and they have a promotion today. So the promotion says, if you can show me on your Fitbit that you have stepped like 12,000 steps today, and I'm gonna pick something here, and your BMR, body mass index, BMI, is below or above a certain point, then we'll give you an extra big Big Mac, because you can have it, okay? It's not gonna bother you, okay? It's a conjunction, okay? It's a conjunction, and it's also an implication. If blah blah blah, then blah, right? Okay. So now the question is, your objective is to get that extra, Big Mac. Okay, what do you need to do? You need to show that you have 12,000 steps on the Fitbit, and a certain BMI, right? Okay, huh? You can rent a Fitbit and then attach it to a dog. For a day. And then you can have extra tapes, because those BMI things, they rely on conductance and other things. So I would assume that there are ways you can attach semi-conductive stripes on your hand, and then just hook up those things to capacitors and other types of filters to trick a BMI machine to think that you have a certain BMI. You can make it bigger or smaller, right? So anyway, those are propositions, okay? So why do we need to understand propositional logic, dealing with McDonald's? Well, because you want a Big Mac, and if you don't get it, you want to know under what circumstances you can sue McDonald's for that, right? So when can you show that McDonald's did not follow through with their agreement? You walked in with a Fitbit, you got at least 12,000 steps. You show that on the BMI machine that you meet the requirement of the BMI, but McDonald's says, sorry, no Big Mac for you today. Then you can use that and go like, hey, McDonald, this is not what you agreed to. I'm going to sue you. So that's one application of propositional logic. But wait, that's not propositional logic. That's just your understanding of the logic. So I don't want to have to use my brain juice to work on all of these things, just to figure out whether to sue McDonald's or not. I want a machine to do it. That is when we get into propositional logic. So you just punch in stuff into a machine, you punch in what McDonald's promised, you punch in what happened in a day, and the machine comes back and say, yep, we got enough to sue McDonald's today. That is what we want. We want automated reasoning. We want automated logic derivation. Is that okay? Not okay from McDonald's perspective, but hey, it has its own army of lawyers. So, are we good so far? All right? So we want to be able to do things mechanically. That is the key. How many people have taken or is currently taking Calc 1 or 2 or 3? Okay? Do you have to prove theorems and stuff like that in that class? A little bit? Okay. How about linear algebra? I think you have to prove theorems in linear algebra for sure, right? Because it's algebra. Huh? For some of them, okay. So how many people have daydreamed of, oh, I wish I could just punch this question into a calculator, and the calculator will show me the proof? You don't have to be shy. Okay, it makes sense. Okay, it makes perfect sense that we want that. So that is the whole thing. Okay, can we make a calculator? Can we make a computer to prove theorems for us? Okay, now this is one kind of specific subset of problems that we can solve. Okay, so later on we will talk about predicate calculus and other things, but this is the beginning. Okay, if I just give a whole bunch of axioms to a system, and I say, well, based on these axioms, things that are true without any question, is that thing a consequence of this? Okay, is it yes or no? Okay, just give me yes or no. That's what we want to be able to do. I think I showed you guys once already. All of this stuff relates to basically, being able to stop something from like this from happening. Pretty sure I showed you before. Heart bleed, yeah? Okay. So we want to basically be able to prove the correctness of an algorithm mechanically so that we can say, yes, this algorithm or this subroutine works in all cases. I don't have to throw a single test case to test it. I know for sure it works so that this does not happen. Okay? So I'll give you the context. This is the context of what we're about to talk about. So now we get into the details. So look at the propositional logic system as a mechanical thing, like a program that you write, okay? So the question is, what are you throwing into the program? What do you give the program? The first thing you give to the program is alpha. This is uppercase alpha, which looks like A. It's basically a set of symbols to be used, okay? So typically we use 0 for false, 1 for true, P, Q, R, S, T for variables, and then we use some Greek letters for what we call schemata. So we'll talk about that later. But basically, it is just defining a bunch of symbols to be used. It's just like in C and C++, you have lowercase a to z, uppercase a to z, and the underscore for variable names. You have semicolon, colon, parentheses, brackets, braces, for punctuations and stuff like that. Okay, so it's not unlike what kind of symbols are legal to use in a particular mechanical system. That's basically what it is. The second one is omega. Okay, omega is a set of operators. Okay, when you read text about propositional logic, they're also known as connectives. So these are your logical operators, like logical not, logical and, logical or, implication, equivalent to, and so on and so forth. Okay, so omega defines basically just how do you connect symbols to mean something. And then you have Z or zeta, okay? So zeta is a set of transformational rules which allows you to look at one particular formula and you say, oh, this formula is really meaning the same thing as that formula. So you can transform one formula from one form to another form, but they actually have the same meaning. I'll give you one example. A and B is the same thing as B and A, right? So if you see A and B, okay, a particular transformational rule may say, oh, okay, B and A is meaning the same thing. That's all it says, or can be implied by. And then I is a set of well-formed formulae. We'll explain what well-formed formulae mean, but it's basically just a set of things that we know are true to begin with. Do not ask me why this is true. It is given to you that it is true. That's all. Is that okay? So I is, or iota, is basically a set of axiomatic truths. Those things are just given to you as, don't ask me why, but this expression is known to be true. Use it as an assumption. So are we doing okay so far with these particular items? So there are 5 items inside a mechanical propositional logic system. Yep. You can use additional operators. You can use any operators. You can basically this is a mechanical system. The question is, does the system reflect actual logic that we care about? So you can have a mechanical system that does not do anything like that, which would not be very useful to us. But so you want to have a mechanical system that does reflect the way that we process logic. Yes. Okay. I mean, you can certainly make one that doesn't model anything that's useful. All right, so we'll use this notation here to basically define what we mean by well-formed formula. Okay. So this is basically saying for all E in A, for every element in alpha, E is automatically known as a well-formed formula. In other words, if you pick anything out of the alpha set, that by itself is known to be a well-formed formula. Okay, don't ask me why. This is how it is defined. This is how we define the base case. So the next line, okay, let me click on that one. Later on, when I give you an example, you will see, oh, okay, this is really easy. The next line basically says, if I give you a whole bunch of well-formed formulae, okay, so phi 1, phi 2, all the way up to phi n are well-formed already. And then you find a connective in omega n. So omega n basically is a set of connective that requires n parameters. So it has n slots to fill. Then C, which is the connective, using the phi 1 all the way up to phi n as parameters, this whole thing is now well-formed. Okay, this is a fancy way to say the following. I'll give you the shorter, not so fancy way of explaining the same thing. So let's say our alpha is defined like this: 0, 1, P, Q, R, S, T. And I'll leave out the Greek symbols for now because they're kind of special in a way. And then our omega is, I'm just going to use the English words. It has not, which is a unary connector. We have logical AND and logical OR. Okay. So this is just the way how I define it at this point. So what this means is 0 is a well-formed formula. 1 is a well-formed formula, P is a well-formed formula, and so on. T is a well-formed formula. Is that okay? Whoops. I keep... So you know that if you use a speaker to replay the video, it might pop your speaker. Okay, I keep getting caught, so I just need to maybe do some cable management. All right. So is that part okay? Every symbol from alpha is automatically well-formed. So now we look at the operators. So now we can say not 1 is a well-formed formula because not only requires one operand, so not 1 is well-formed. We can also say, I'm going to use the infix notation here. So P and Q is a well-formed formula because it has two sides, n has two sides, and I'm supplying well-formed formula to both sides. I can also say P or 1 and Q or Q is a well-formed formula. Is that okay? This is the recursive nature of well-formed formula. P is well-formed, 1 is well-formed, so P or 1 is well-formed. Is that okay? Q is well-formed, Q is well-formed, Q or Q is well-formed. Because P or 1 is well-formed, Q or Q is also well-formed, that makes the entire thing also well-formed. Is that okay? So you can derive a lot of well-formed formula that may not be very particularly useful. For instance, you can say 0 is well-formed, 0 and true, false and true is also well-formed. Right? This thing is also well-formed. This thing is also well-formed, and so on. So if you look at the space of well-formed formulae, it is infinitely large. Because you can keep attaching and 1 to continue something that is actually just saying false. Because false and whatever is going to be false, right? So you can keep attaching and true and true and true and true to this whole thing. In the end, you still only get false. So it's kind of pointless. Well, just because it's pointless doesn't mean it is not well-formed. So you have a space of well-formed formulae that is basically infinitely large. That becomes really important in the future because your so-called well-formed formulae space is your haystack. The theorem that you want to prove is what? The needle. So you're trying to find a needle in a haystack. But it gets worse. It is not like we know the needle is in a haystack, go find it. We don't even know whether the needle is in a haystack or not. So now you have a big problem because the nature of the problem is to find the needle in a haystack. You have an infinitely large haystack, and we don't even know whether the needle is in a haystack or not. So what kind of problem do you think you might run into? You cannot conclude. You can keep searching and searching and searching, but you can never come to a conclusion whether it is the first case where the needle does exist, I have not found it yet, or the needle actually does not exist in a haystack, but since it's infinitely large, I can never confirm that. Okay? So later on, we'll find out ways to fix that problem. Okay? So are we still doing okay so far with this particular discussion? What is a well-formed formula? Yep.
So you should never use an operator in a way that it shouldn't be used. Like an operator.
Yeah, basically that's what it means. So we are defining the syntax of what expressions should look like. It's just a fancy way of defining that. But so far we are just defining the symbols. So going back to the example here, if I can make A like this, omega like this, for now we'll leave zeta out of it, and we'll talk about iota a little bit. So iota basically says true is true by definition, not false is by definition true, and then you can throw in other things too. You can throw in something like, oh, I'm just going to tell you that P implies R is true. I will also tell you that S or T is true, and so on. Why? For no particular reason. I'm just making certain assumptions and say these well-formed formulae are known to be true. Yep.
In I, can you also have things that would like contradict what we would normally assume from like our truth tables? Like if you have like not false is actually just false.
You mean can iota itself create a contradiction?
Well, what I'm saying is the rules in iota have to match what we would normally use for the rules in terms of like truth tables.
Does not have to.
Okay.
All right. So the bottom line is, iota is really just a set of well-formed formulae that are assumed to be true. Okay, and the axiomatic ones are not as important. It is the other ones that make use of the variables that are kind of useful. So what can we use here? So in our system, these things would be basically so a variable would be a proposition like, did you have 12,000 steps on your Fitbit? That's your variable P. Okay. Does your BMI meet the requirement that McDonald has already mentioned? That's variable R. Okay. And then T is going to be PQ. Oh, okay, that's PR. I'm missing Q here. So Q is you can get a free Big Mac of that day. That's Q. So all of those can be true or false, right? You may not have 12,000 steps on a particular day. So all of those can be true or false. But what I'm going to put into iota in this case is P and Q. P and R implies Q. If you have at least 12,000 steps on your Fitbit, you meet the requirement, your BMI requirement, then you should get a Big Mac of that day. Okay? That I'm going to put here. Am I going to put P into here? May or may not, okay? Depending on whether I want to make the assumption that you do have 12,000 steps of that day or not. Okay? Yep.
Whatever's an I, we have to work around, right? But we should always include whatever's an I when we're coming up with.
We are not working around. Okay, so let me give you another kind of mental picture. So the mental picture is kind of like this. I'm thinking about whether to do it on the projector or not. I think we can do it on the projector. So the mental picture is going to be, I'm just going to use this here. And it's useful to make it match the size of the underlying window, so I don't accidentally click on something outside of it. There we go. Okay, so when you look at the so this, let's say this is the well-formed formula space. Okay, so this entire thing is the well-formed formula space. And then we have the green dots here. I'm going to use the dark green here. Those are things in the iota, because everything in iota is a well-formed formula. Is that okay? So I have several things that I put a finite number of things that I'm going to put here as my green dots. So the green dots are in the iota. So I can also write here. So iota is green. And it's finite. So using the transformational rules from zeta, what we can do is we can say, oh, okay, using that transformation, I can now confirm, I'm going to use blue here. So I can now use a transformation rule to basically say, if this well-formed formula is a green dot, is in iota, this follows. I can imply the blue dot because of the green dot. That's what the transformation rules are for. So we can basically start deriving things, and then the blue dots, can connect to other blue dots too. And then occasionally you can have mergers between these two. You can have two green dots going to one blue dot, and then you have two blue dots going to another blue dot, and so on. So we are labeling things. Okay, your well-formed formula space is already there. It's just like the universe is already there. What we are trying to find out is, can we make a connection to the theorem that we want to prove? So the theorem that we want to prove is a well-formed formula. Okay, so what I said a little bit earlier is not entirely correct, entirely accurate, and I'll talk about that. So let's say that's your theorem, okay? Your theorem has to be in the well-formed formula space because your theorem itself has to be well-formed. The question is, can I eventually make connections to here? Starting with the green dots. That is the question. Is that okay? So you can look at the green dot or the elements of iota as the seeds of this entire universe. And the question is, can I, based on the seed and based on the transformational rules, can I eventually make a connection to the magenta dot, which is the theorem? So I was a little bit incorrect earlier, that I said, the needle may not be in a haystack. The needle is there. The question is the connection to the needle there?
So mistakes come into play when you make a illogical connection or something like that.
Well, if it's a mechanical system, then it cannot make the mistake like we can make a mistake, like a careless mistake. But the mistake can be made when your transformational rules are incorrect, or when the green dots are not, what the green dots really should be. So you're starting off with the wrong assumptions, or your transformation rules are not consistent with actual logic. We'll talk about that pretty much close to the end of the discussion of propositional logic, but that's a very good point to consider. So are we doing okay so far? So we have talked about everything except for the blue lines, okay? What does a particular transformation rule may look like? It's called an inference. So another name of a transformational rule, an element of zeta, is known as a inference. So an inference looks like this, okay? So every inference is going to look, kind of has this form here. So this is the first time we get to see the Greek symbols. In this case, we have psi 1 all the way up to psi m, and this particular symbol says infers. It infers phi. So what that means is all of these things, now this is really kind of abstract at a higher level, but what all of these things are basically specific forms of equations, and we can say, okay, those things transforms to this. I'll give you an example. So instead of looking at a very abstract description of a particular transformation rule or inference, let's take a look at one that is concrete. So a concrete one may look like this. So it's always a set on the left-hand side of the inference, and you can start with something like this. So we can have phi. Okay, we can just do a simple one. Phi or psi, and this is the only element. And then we can say it infers the following. What does it infer? Psi or phi. Is that okay? All this is doing is to express the commutative rule of Boolean algebra. Ordering does not matter. You can flip the right-hand side and the left-hand side. That's all it does. So this is what it looks like. You can also use something like this. You can also say phi implies psi, comma. Okay, this is a comma in a set, and phi. What does it infer? Psi. Okay, so what does it mean? It means if of all the well-formed formulae, okay, if you already know something, a particular well-formed formula of the form of something implies something else is true, okay, so you know the implication itself is true, but you also know the left-hand side of the implication as a condition itself is true, then you can infer that the right-hand side of the implication is also true. Okay? You can do something like this. You can also use a transformation rule that may look like this. Okay, it's still based on the implication. So you have phi implies psi. Okay, so for whatever reason you find a well-formed formula that fits this particular format to be true. It can be in the iota itself. It can be derived from something from the iota. It doesn't matter. Okay, if you know a well-formed formula that looks like the form of phi implies psi, which means I don't really care what is phi and I don't really care what is psi. It's just a placeholder. Okay, and you also find out that the negation of psi is true. Once again, I don't care whether it comes straight out of the iota set or whether it is derived, but for whatever reason, if you can show me that the well-formed formula, the negation of psi, which is the same as this psi here, is also true, then you can infer that the negation of phi is also true. Okay? So you basically come up with a bunch of rules like this. Now, there are some really oddball ones, which will kind of make people cringe sometimes. You can start with an empty set. I don't need to know any particular well-formed formula to be true, but then I can infer the following has to be true. You can always infer that phi or not phi is true. And it doesn't matter what phi is. Phi can be any well-formed formula in that entire well-formed formula space. And now you can claim that is true. And you can just kind of imagine how this by itself can give you a really infinite space when it comes to things that can be labeled true. Is that okay? So basically what we'll end up doing, if this is the direction that we are going for, is we study Boolean algebra, okay? And then we turn every single axiom in Boolean algebra into a rule like this. And that becomes the propositional logic system. The biggest question is it actually going to be useful? In other words, if I say a whole bunch of things using propositional logic, and I say, well, based on all of these things that I give you in the iota set, does this statement follow? Does it follow that that has to be true? Then the system will have to choose which rule to apply, because at any particular time, a whole bunch of rules are applicable. Well, just because a particular rule is applicable doesn't mean it's a good idea, right? So an automatic system can choose the wrong path, so to speak, at every single turn and just end up burning CPU cycles and not get any closer to the actual proof. And that is the problem of propositional logic system, is it is assuming that whoever is choosing which rule to apply is smart like a person, like an experienced mathematician or logician, which is a flawed assumption. Is that okay? How many people have taken a class in algebra of some kind? I don't care whether it's just algebra or linear algebra or abstract algebra or Boolean algebra. Okay, most of you have. So what is the biggest problem of a proof in that class? I mean, there are only so many axioms, right? There are only so many rules to apply. So when your professor asks you and say, I want you to prove that based on these assumptions, this implies that. What is the typical problem that you run into? Assuming it's open book and open notes. You don't even have to memorize all the axioms. It's choosing which axiom to apply, right? So when you read the proof or the solution from the professor, it's like, oh, 6 steps, that's all to it. But when you are doing it, every single step seems like forever, because there's so many things, so many rules that are at the same time applicable. Some of those are useless, okay? It will give you a different form of the same formula, but it doesn't get you any closer to the solution. So the question is, how does the professor know exactly which 6 steps to perform and in what particular order? And why would a person who is less experienced not know how to do that? That is the question. What do you think? I mean, what is the difference between you and your algebra professor or teacher? Experience, very good. It has nothing to do with well, it doesn't have a whole lot to do with intelligence. It has a lot more to do with experience. I certainly hope that you guys are all smarter than me. Think about it this way. If a professor tells you, I'm smarter than you because I'm the professor, and some of those students become professors too and say exactly the same thing, what's going to happen after like 6 quote unquote generations of professor and student? It can only go downhill, right? So I definitely hope that you guys are smarter than me, and some of you smart ones and careful ones and disciplined ones will be programming the firmware of my pacemaker. Because I don't want, the heart bleed bug to be in my pacemaker. That would make it very funny for people who are watching, but not so funny when it is inside of me. But anyway, it has to do with experience. Now, when you're looking at a computer using a formal system and a computer mechanical way to prove theorems, does the computer have experience in the same way that we have experience? It does not, okay? Now, that might change, okay, because of the way we apply neural nets and deep learning. It might be able to teach a computer kind of the same way that we teach a person and gain the experience, but that is not done yet, okay? So that means, a propositional logic system that is trying to mirror Boolean algebra, okay, using these particular transformation rules, may not be very productive, may not be very useful. Is that okay? So what we need now, okay, we are close to the end of today's class. We got 1 minute left. So what we need is a particular way to express the same thing, okay? If we have a particular way to express a Boolean expression, we want to find a way to express all the Boolean expression, all the possible Boolean expressions, okay, so that it is easy to process mechanically. Instead of using multiple transformation or inferences like this, we want to single out maybe 1 or 2, okay, that we only apply. But most importantly, we want to reduce the space of all well-formed formulae to a finite space. Because instead of saying, guess what? The haystack is infinitely large. I have no idea where the needle is. I can now tell you, the haystack is kind of big, but we know how big it is. It is finite. Now I want you to find the needle in it. That's a doable problem, right? Because it's just a matter of time. But if the haystack is infinitely large, it is not an issue of do you have enough time, because you may never find it. Is that okay? So your assignment before Wednesday is to work on the assignment that is due on Wednesday, but also to read ahead of me. If you can get to CNF, conjunctive normal form, and resolution, that'll be great, okay? I'll see you guys on Wednesday. Yep, hold on a second.